Hey, so I'm George, and I wanted to talk real quick about a recent adventure I had in making some code go fast. The specific thing that I was working on was 64-bit integer multiplication, because I write a lot of crypto code. That's a thing you need to do when you're multiplying big numbers together. But of course, 64-bit numbers multiplied together are going to give you 128 bits of output, which we can't natively represent on a 128 or a 64-bit machine. So you have to store the results of these big multiplications in two registers or two variables, and then you can kind of add them together in the right context to get your final result. Processors do this for you. They have like widening or expanding multiply instructions that will just do this for you. And some languages take those features and build 128-bit integers on top of them. But Go does not. So in Go, if we want this, we have to write our own multipliers. And the actual details of this are not important. It's a bunch of like bit shifting stuff, but it fundamentally is splitting up the numbers into subunits that we can more easily handle as 32-bit values that'll overflow cleanly into 64-bit ints. In practice, you have seen this before. It's just multiply and carry like you did in school. So when we benchmark that, though, we'll note that it's actually much, much slower than it properly should be. Because if you think about the idea of like an assembly instruction that does this multiply, it should be essentially too cheap to meter. But that's, and admittedly, this is a benchmark from a Chromebook, but still, that's 13 nanoseconds, which is when you do dozens of these in a row, is a really human noticeable amount of time. When in fact, it should be something that doesn't even show up on benchmarks. So when things are too slow, we go to the profiler, right? We look and we see, like, where are we spending all of this time? And here, it's returning that array at the end. That's like the bulk of this. So, all right, we've identified the slowest thing. Let's fix it. Let's just not return an array. We can use two values instead. And benchmark this. That's 9 or 10 instead of 13 or 14. It's better, but still not great. So we have two versions of this where we fixed what appeared to be the biggest problem, and in fact, it's still really slow. So we need it to go fast. Let's write some assembly. And like I mentioned, there are processor-specific instructions for this. On AMD64, it's mulq, which just multiplies two quad words together and puts the output in RDX and RAX, the two registers that I mentioned earlier. A Go assembly function that uses this looks like that. This is nothing clever. It's just a direct call and a return. It could probably be more efficient, but that's beside the point. So when we take this assembly multiplier and benchmark it, we notice that it's about twice as fast, but it's still like a countable number of nanoseconds per op, which is, again, not right. So we've written a whole bunch of different like versions of this function call, and if the function isn't really the problem, then we're left wondering what's happening with the call. So we're back in our profiler, and when you look at how these benchmarks are rendered in assembly, you can see that it moves the arbitrary large numbers onto the stack, then executes a full function call. And in fact, in Go, for various reasons, function calls are pretty slow. And specifically for this class of like small arithmetic function, the couple of nanoseconds that the call itself takes to move registers around and stuff is going to completely dominate the runtime. And Go actually does solve this, as most languages do, because compilers do something called inlining, where they take the code from sufficiently small or simple functions and move them directly into the caller function. And the Go inliner lives at this address. I'll post the slides in a bit. But essentially what it does is it walks through the AST of the functions at build time and calculates a cost that roughly correlates with the complexity of the function. And if the cost exceeds a certain number, a certain budget, then the function won't be inlined. And if it's less, then it will. The specific rules that the inliner uses in Go is this. Each instruction in the tree is worth 1 cost, and then some instructions cost more than others, particularly stuff around slice ops. Pretty much if you're using slicing heavily in your function, it will not get inlined. And very recently, the inliner has been changed so that direct function calls are okay if the target itself is inlineable and we have budget for the function body. Previously, the inliner only worked on leaf functions, but now there's a little bit more wiggle room. And then some things are completely hard stops. Interface calls, type conversions, anything to do with panic or recover, certain functions in the runtime package, and what bit us earlier, anytime you want to call a function that was implemented in assembly that's not a compiler-recognized intrinsic. So if you saw math.bits in Go 1.9, this limitation is why that needs to exist. And now that we know about that, we can kind of look at our multiplier from earlier and think, well, how can we get rid of some instructions? How can we give this a slightly simpler syntax tree? And the most obvious thing is to take some of these variables that we only use once and propagate them. We can get rid of several assignments, and it turns out that this is good enough to simplify this function to a point where it will inline. However, we really just sort of like stared at this and thought and like tried some things until it worked, which is not a very repeatable process. The compiler does keep metrics for this, but it doesn't expose them even in debug mode. So I've got a sketchy patch on GitHub for the Go compiler that will output the costs of all of your functions at build time. And the magic number is 80. So you can see that the first 2 versions of the multiplier were up in the 90s somewhere, and then right as we simplify things enough to get below 80, the compiler will very helpfully tell us, yes, I can inline that. And in fact, the results are pretty dramatic, because when we benchmark that inlineable function, instead of somewhere between 5 and 15 nanoseconds per op, we get 1, which is a pure Go function running in 1/5 the time of our fancy assembly multiplier. However, you can't take this as license to write unintelligible code just because the inliner told you to. Once you get past the threshold of lower than 80, the inliner metric no longer correlates to any notion of performance. So this is, according to the inliner, a really simple and straightforward function. But when you benchmark it with inlining, you see that it's actually the exact same level of performance as the much more readable code we just saw. And if you benchmark it without inlining, like with that disabled, it's closer to 10 nanoseconds an op. So you would be better off taking the function call overhead to use the assembly. And that's what I got. No time for questions, but I am on Twitter, and all of the example code is on GitHub. Thanks.